9, and several of you having trouble with a lot of these problems, so I'm going to do quite a few of them here. So number 3, it says that we want to write f of t, which is given as 5 times 7 to the t, as a function of something times e to the kt. Well, 5 e to, what would be another name for 7? Well, that'd be e to the ln 7 to the t, and so that's just a number, so it'd be 5 e to the ln of 7 times t, or if I want the approximation, I can calculate ln 7, and I can write it 5e to the 1.9459 t. Okay, that's all I wanted you to do. On 6, it said P obeys the exponential growth law. Find a formula for P of t. The population after some time is equal to the population at the start, e to some kt. And t is in years, and in 7 years, and the doubling time is 7 years. Okay, so we need to work with this, and it says, also it says in there, P of 0 is 100, so the starting population is 100. So that's 100, but that's not important for figuring out the K, which takes 7 years to double. Now, they give you another way to do this, but I'm going to show you this way. If this is going to double, this has to be 2. So e to the kt has to be 2 for the doubling time, and they said that was 7 years, so 2 equals e to the 7k. Taking the natural log of both sides, we get ln 2 equals 7k, and so the constant is ln 2 divided by 7 years is the k. And so if I want to figure out that, ln 2 divided by 7, if I want a decimal value, then the equation would be 100, because that's the initial amount, e to the, I could put in ln 2 divided by 7, but I'm just going to write in 0.099 t. So it's basically 0.1 t. That's 6. Now let's do, after 6, how about 9? 9 says, find the solution to y prime equals 3y. Well, and y of 2 equals 1,000. So there's a couple of different ways to do it. The book does it one way, but I'm going to write it as, well, the only function, y, that its derivative is just a constant times y, is the function y would have to be something like y0 e to the 3 times the variable, let's say it's t. Because the derivative of this would be the same thing, the original y, times the 3 because of the chain rule. So then it says when I put in 2, I get 2 in here, I get 1,000. So I can figure out y0 here by saying, well, if it's 1,000 when e to the 3 times 2, so e to the 6, so y0 is 1,000 divided by e to the 3 times 2 is 6. And that is 2.478. So y would equal 2.4788 e to the 3t. Now let's just check and see if this comes out to be 1,000 when t is 2. So that'd be that number times e to the 6 is 1,000. I mean, that's how it would have to work. And so there's the equation. Now, instead of doing that, they just did a t minus 2 and then put 1,000 here. And then when I put in 2, I get 0. 3 to the 0 is 1 times 1,000, makes it work for 2. But this is another alternative for doing it without the minus 2. Okay? And then 12. Let's see here. I gotta make sure I can see this. The computer's being strange here for a moment. Okay, so now I'm going to do 12. I'll move this up. And 12 says, come on, turn the page here. The half-life of radium-226 is 1,622 years. Okay, so find the its decay constant. Well, okay, so that means e to the kt when t is 1622 has to be 1/2 because it's half of whatever it was. So ln of both sides, ln of 0.5 has to be k times t, 1622. So if I divide by 1622, I get the constant. So that's ln 0.5 divided by 1622. And the decay constant is 0.000427. 0.000427 and negative. That's the decay constant, so that the half-life is 1622. And then we have 15. And the reason we're doing all these things is this e to the kt is the only function that satisfies a differential equation where the change is equal to some constant times the original value. That's why these are all in here. Okay, 15. 15 says population of a city is given by the formula P of t is equal to 2 e to the 0.06t, and this is in millions, so this is like 2 million is the starting, where t is measured in years. Calculate the time for the population to double. Okay, so this would have to be 2, and we don't really care about that. Or we could put 4 here, which would be double that, divide by 2, and it'd be 4 divided by 2 is 2. This has to be 2. And then if you do the ln, we're going to get ln of 2 divided by the k, 0.06, and that will give you the time to double. ln 2 divided by 0.06, and that's 11.5 years. Actually, that rounds to 11.6. And then it says triple. Well, then this would have to be 3. So it would be 3 in this spot. So it would be ln 3 divided by 0.06. And that would be 18.3 years. And then it says, how about to be 7 times? So it would be ln 7 over that. Bring that back, divided by, and change that to 7. And we get 32.4 years. Okay. And now we're on to, let's do 18. Several people asked about this. And it says, if light enters some kind of material, could be water, could be dirty water, could be plastic, and the further the light tries to go in through the material, the more the material absorbs the light and it gets less intense as you go in. And it says the intensity after you go into some thickness, where this is how far it goes, is equal to what it is outside e to the kt. Now they say k is equal to, what was it, 4 m to the minus 1, which means 4 per meter. So in the t is the thickness, this is how many meters in we go. Times this would give us the intensity, the intensity left if there's some intensity at the beginning. So this is, the equation is e to I0, e to the 4, and its intensity is decreasing, so we have to put minus 4t. Now, the question is, how thick must the block be to reduce the intensity by a factor of 1/3? So we want this to be 1/3. So we're going to have ln of 1/3 divided by the k. The minus would go up here and change that to ln 3 divided by 4, but we can type it in either way. I'm just making it easier to type in. ln 3 divided by 4, and we get, it would have to be 0.274 meters thick. Okay, let's go to number 21. Says degrees in physics from 1955 to 1970. The degrees grew exponentially with a k of 0.1. So the number of degrees after so many years is equal to the initial number of degrees e to the 0.1, and it grew, so that's plus 0.1 times the number of years. So there's an equation. How long will it take for the number of degrees awarded to be increased by 14-fold? So we want this to be 14 times what it originally was. So it's, again, it's just going to be ln of 14 divided by the k, 0.1. Which is 26 years from 1955. That's how long it would take. So that would be 1981. There would be 14 times as many degrees as 1955. Or 26 years beyond 1970, when there'd be 14 times as many as there was in 1970. Once again, to see how that is, that's 14 has to be e to the 0.1 t. And so if you take the log, we get to ln of 14 equals 0.1 t, and then you solve for the time that it takes to get to 14 by dividing both sides by 0.1. And that's how we get that time to be 14 times as much. Okay, now it's part A. And part B says, if 2,500 degrees were done in 1955, when would there be 10,000? So we just have 10,000 goes 2,500 e to the 0.1 t. So if we divide this by 2,500, not 25,000, 2,500, this is 4. So we're just trying to figure out the time that we get 4 times as many degrees. And so that's just going to be ln 4 over 0.1. Which is 13.8 years, 86 years, about 14 years past 1955, which would be 1969. There was about 10,000 physics degrees. Okay, on to, let's see, next one. Sorry, I got to get my music to stop here. What happened? There we go. Oh, that's always fun in here. 24. 24. This is about the caves. And I was corrected a little bit, but the carbon-14 decays, and when it's gone, there's less of it as time goes on. Now, when we're alive, we're breathing in air that has about, they said, 10 to the minus 12, which means 1 in 1 trillion one molecule out of every trillion carbon molecules is carbon-14. That's what's going on in the atmosphere normally. And so any living thing that's breathing in air, it's going to be taking in carbon, and it's in all their plant life, and so we eat stuff and they'll be coming in that same ratio. So this is the existing ratio. And it says the amount of carbon left after some time is equal the initial carbon E2, and they tell you the decay constant for carbon-14 is 0.000121 T, and it's decay, so it's minus. Okay, so in this cave, they dated stuff, and they said it had to be somewhere between, what was 29,700 years ago and 32,400 years ago. So what would the fraction of carbon-14 be, the ratio be then? Well, that would be simply this fraction of that. But we have to put this in for the t. So I'm going to type in here E, come on, turn on here, e to the negative 0.000121 x and ignore that. Now I'm going to store in X 29700. Okay, so now I'm going to find out what that is. I'm just going to go back to it. And now the X is the correct X, and there'd be, this would come out to be 0.027, 0.027. So about 2.7% of what it originally was. So if I take that times 10 to the negative 12, I find out the new ratio. And so that would be that answer times 10 to the negative 1, 2, and I get the new ratio of 2.7496 times 10 to the negative 14. And the other, that's how the ratio they found, which is less than it is currently. And that makes sense. It decreased by a certain amount. And the other end, we'd have to go back here with X being, what was it, 32,400. Store in X, and then I can go back and figure out that with that X, and that would be 0.0198 times 10 to the negative 12, which is 1.98 times 10 to the negative 14. So somewhere between here and here's the range of carbon-14 ratio to carbon regular in the material that they found in the paintings in the cave. Next one, 29. 29. This is where they had that big table, and I did that one for both classes, so I'm going to skip that one. And then I'm going to do 33. And 33 said, compute the balance if, after 10 years, if $2,000 is deposited in a 9% interest-bearing account compounded quarterly, monthly, and continuously. Quarterly, monthly, and annually, or continuously. And this is at a rate of 9% and for 10 years. Okay, the quarterly and monthly all work off of the formula that says it's the original amount, 100% of the original amount, plus, I want to be able to see here, make sure you can see it, so I got to move a few things on my computer. Okay, good. 1 plus the interest rate, 0.09 quarterly, that's 4 times a year, to the 4 times the number of years is 10. So typing that in, we get 2,000 parenthesis 100% of it plus 0.09% divided by 4, because we only get a quarter of that every quarter of the year, to the 4 times 10, which comes out to be $4,870.38. $4,870.38. Now, if I'm doing it monthly, the 4s become 12s. So I can go back here and just adjust my equation and put in 12 here. And for that 4, put in a 12. And I get 490271. Now continuously, then I have to use the formula 2,000, the initial amount, e to the interest rate 0.09 times the time t, 10. 2,000 e to the 0.09 times 10. And I should put that in parentheses. Don't have to on this calculator, but if you're doing an 80 older calculator, you need to put that in parentheses, and we get a little bit more if it's compounded continuously. 491921. Okay, now we're going to go to 43. 43 says a computer system costing $25,000 reduces the labor cost $7,000 a year for 5 years. Is it a good investment if the R is 8%? So let's see. So the amount you save, you got to figure out for each year how much you would save in the present value. So the present value, 7,000. Back it out for the 1 year that you would have to wait for that. And so if it was growing at 8%, then to back it up would be minus 0.08 times 1. And then the second 7,000, you'd have to wait for 2 years. And to back that out, it would be e to the minus 0.16, because it'd be so that would be 1 year. And this time the t is 2, so it'd be 0.1 that. And then the third 7,000, we'd have to wait. And how many of these are there? 5 years. It would be 0.08 times 10 to the 5. So that would be minus 0.08 times 3 years is 0.24, plus the next 7,000 be e to the minus point, so 24, 4 times 0.8 is 32, plus e to the minus 5 times 0.8 is 4. So one of the 7,000 for 1 year, one of the 7,000 for 2 years, one for 3 years, one for 4 years, and one for 5 years. And we would get, let's see, I think they do that, show all of that in the book. Yes, they do. It comes out to be in the answer at the back of the book. $27,708.50. So that's how much money you would save. Now they're saying you would have to spend $25,000. Well, the value of the savings, the money return in present value would be 27, and it costs you 25, so it would be a good investment. And in current dollars, it's going to save you $2,708.50. Just that minus the 25,000. Okay. And then 47. So now we're doing a problem where they said you got $5,000 that you get increasingly, you get money back. So it's happening continuously. So there's a formula for one that's continuously coming back, and it says the present value will be the integral from 0 to however much time of the formula for the value going down. So that's going to be 5,000 times e to its going up at 0.1 t. Now the value of it, that's later, and when you work out the costs, they're saying that is e at a 0.505%, 0.05 t dt. Now what's different about this one and the last one, this is continuously changing, and we actually get some calculus on this one. So we got, and they said for 7 years, was it? Yeah. And they said make this 0.5, and this is how fast it's growing, but this is how much you're losing because of waiting for it, the money. So we get integral from 0 to 7, 5,000 can come out, and this e to the 0.1 t, oh, and this is decreasing, so you got to put a minus on it, and e to this, and so you add the powers, so 0.1 minus 0.05 is e to the 0.05 t dt. That integral becomes 5,000 e to the 0.05 t divided by 0.05, evaluated from 0 to 7, and that becomes 5,000, and then we get divided by, I can take this out, divided by 0.05 times e to the, put a 7 in there, you get 0.35 minus e with a 0 in for the t, it's e to the 0, which is 1. And so 5,000 divided by 0.05 is, just so you can see it, 100,000. And e to the 0.35 is 1.419 minus e to the 0 is 1. So that's going to cancel the 1, and so we're going to get 0.419 times 100,000, which is, move it 5 places, so it's going to be 41900. 1, 2, 3, 4, 5, 2 zeros. And that is the present value. Okay. So the value down the line is going to be worth $41,000 today and $900. They actually have, if I keep a few more decimal places, 90675, and I think that's what they have in the back of the book. Not rounding it off.